I don't get this introduction every day, but I will from now on. My name is Gunnar Grimnes. I'm here to give a talk about arming the enemies of Facebook and Google. Our CTO made up the title. I'll return to the title in a minute. So the big picture of this talk is really big data. If you didn't live under a rock recently, you've heard of big data. There's been lots of talk of big data today. It's a great new thing. It's going to solve all our problems. Now I must confess, for me, it is not so much about the big data. It is more about data in general. It can be small if it's good data. To me, it's more about machine learning. It's more about what you do with the data. And this is all my focus on the big data thing. So I'm not going to talk about massive Hadoop clusters of terabytes of data. I'm just going to talk about data and machine learning. Still, the promise remains. The promise of big data, they're great. I've picked out a few things that are relevant to what we do, but it's going to give you better ways of understanding your content. You're going to have better indexing. You're going to have better search. You're going to have better navigation. You're going to have more intelligence. It's going to have personalization. It's going to have recommendations. It's going to have finding related content. It's going to have actionable insights, if you love your buzzwords. And all of this is great. All it needs is a team of data scientists, and you put them in a room and you give them all your data, and wonderful things happen. You have a team of data scientists, right? 200 people? Because Facebook do, and Google do. And they fight now to hire all the big rock star machine learning professors, get picked up by Google and Facebook and Yahoo and this Chinese company I forget the name of. The problem is, we're a small country, it's Norway, we have comparably small companies. Not every company can afford a team of data scientists, and not every company can afford to hire a rockstar machine learning professor. So here we come to the point of the talk, the enemies of Facebook. The question is, how can we empower these companies that are not Facebook and not Google? They do not have a massive research budget, they don't have all these people. And this, for us, is an interesting problem. So some of the enemies of Facebook that we often come across is, for instance, media companies. Media companies are enemies of Facebook in more than one way. It used to be the way that you went online, you went to the front page of the newspaper, you went to Aftenposten or to the BBC, you would read your news, get it from the homepage, and stay there for a bit. It's increasingly less like this. People get to the news not from the front page, but they get there from links from Facebook. And many people never leave Facebook at all, or like they never click on through to the news. People get their news from Facebook. And of course, you all know the way that the sales of newspapers is going. And earlier this year, there was an interesting report from the New York Times. They are struggling, like all standard media, that the print newspaper is going downhill, and they try now to build up the digital one. And they leaked this innovation report where they pointed out that there has to be a culture change now. They have to change from being an impressive paper newspaper that happens to have an online presence, like it was fine in 2000, this was perfect. Now they really have to change to become a rich digital platform that happens to have a paper newspaper. And we think, of course, that this big data and this machine learning, like making the most of your data through automatic analysis is crucial. Luckily, this is the arming part. The good news is that all these machine learning people who do all this research, especially machine learning, there's a big focus on reproducible science, and there's more and more focus on the engineering part of things rather than just writing algorithms. And it turns out they put all these things on GitHub. Whenever they make a fantastic new algorithm at Google or Facebook, either they put it on GitHub or someone else will read a paper from Google Scholar and implement it and put it on GitHub. So this is what we noticed. I keep saying we, but the slide comes a bit late. I come from a company called Bakken & Beck. We're a digital agency in Oslo. We work with all these newspapers. I have a machine learning and artificial intelligence background, so I knew all these GitHub repositories, and we thought, let's take all this code that is already there, take this data, take these methods that are so known, put it together to help our customers, the news agencies and other customers. And we made Orbit. Orbit is a brand new company. It was officially funded last week. But what we made is we've made a collection of natural language processing, so text analysis services, available in Norwegian as a software as a service. I am not here to give a pure marketing talk today. I could talk about how great Orbit is now for the next half hour, but instead I'd like to take a step back and I'd like to look at the open source tools that we used to make this happen. So we started Orbit, we started thinking about this maybe 1 year ago. I sat and I looked at GitHub and I looked at these things and I pulled all these things together. And I'd like to quickly outline a few of the tools and a few of the techniques we used to make it happen, so that you can go home and build your own Orbit over the weekend. So what we did. I'm going to talk mainly about this because I find it to be the most interesting thing we've done. This is something called entity extraction. It identifies people, organizations, and places, and other types of things in text. Essentially, it goes from this. The example is in Norwegian, because Orbit works in Norwegian. So in Geneva, Barack Obama gave a speech to the General Assembly of the United Nations. You get a bit of text. What you want the algorithm to do is to go through the text and find out Geneva is a place, Barack Obama is a person, and the General Assembly of the United Nations is an organization. Right, it sounds simple, but it's not quite so simple for the computer. So, of course, machine learning was on the second slide. The thing is to really, I don't want to sit down and program this myself, because it's very, very boring. And it will be time consuming and I'll get it wrong. It's much better to give it to machine learning algorithms and say, right, this is what I want. The problem is, for machine learning to work, I need examples of correctly tagged sentences. Luckily, someone has gone and made Wikipedia. Wikipedia has lots of text, and it has lots of entities. For instance, here's Barack Obama and his Wikipedia page. This is all fine. We can find lots of pages of Wikipedia. If you scroll all the way down on the Wikipedia page for Barack Obama, you'll find a list of categories that Barack Obama is in. In this case, he's in a category called Barack Obama, his birth year, he's in a category called living people, etc., etc. What I did was I collected all the categories from Wikipedia, and I manually classified them, so semi-manually classified them into the types of entities I was interested in. So I said, all the things that are called 19-something births are people, all the things that are places in Ukraine are locations, etc. This was a manageable amount of effort. There's maybe 10,000 categories that have more than a certain sensible amount of entities. So this was a good place to get type tags that was interesting for the different pages. Then we go back to a different page of Wikipedia, in this case Vladimir Putin, but it's random. And in this page, you'll find a sentence where it links to Barack Obama. So this has Barack Obama meets Putin at his dacha outside Moscow. Now this sentence I can take as a training example for my entity extraction, because here I have a sentence of text, and I know that Barack Obama is a person, and I know that this particular text is a link to Barack Obama. And there we have it. There I have my name entity recognition training data. We do this for Norwegian Wikipedia. You massage it a bit to find more links, because not everything is linked. And then without much hassle, you have between 500,000 and 1 million training examples. And then you get somewhere, because then you can start casting this as what is called a sequence classification problem. So you look at each word in a sentence. Sorry. And you tag it. This is a type of tagging. You want to tag each word. So either it's O for other, it's not one of the types you're interested in, or it's B location, beginning of a location, or it's B person, the beginning of a person name, or I person in the person name. This gives you a way of tagging each word, or like you can tag a word at a time, but still get composite words tagged. So you still tag Obama as a whole thing. So this is great. Now you have the class you want to predict. And then you start thinking about the machine learning algorithm needs something more than this. It needs some way of knowing something more about the words that you have. So you start making up features. So you look at some things and you say, well, I, the Norwegian in, is a single letter. It's a capital. You can add these as features. You can add a capital for every word that starts with a capital. You can add mixed case for things like FNs. You can tag the last word of the sentence. You can make up lots of different features. You can tag the prefixes and the suffixes of each word, and all of this is more information for the machine learning algorithm to make something up. The problem is, for a human that would go and do this and say, is Barack Obama a person? What carries the most meaning in this sentence is actually the actual words themselves. The problem is, of course, that for the computer, the words carry no semantics. They're just a random label. It will use the words as a sequence, but it doesn't know what it means. So instead of saying gave a speech, it will just have some random string of letters. They're good. The good point is that the machine learning scientists have already sort of thought of this problem. And kært barn har mange navn, so beloved children have many names. And someone made up something called word embeddings, or word feature vector representation, or distributional representation. It's essentially a way of taking, based on a large amount of unlabeled text, you look at the words and you put them in a massive n-dimensional space. I think this is, here the massive dimensional space is 2-dimensional. And what the algorithms do is they will take the words and they will look at the context of the words. And they will group words together, meaning put them in the same area of this dimensional space if they appear in a similar context. What this means is that you end up grouping words that have similar semantics together. So you get all the verbs together, like you have a cluster here for verbs that are sort of said, expressed, various synonyms for this. You will get things like the days of the week will cluster together because they always appear in the same context. Political parties will appear together, adjectives, etc. And this means now in the end you'll end up with maybe like 50, 100, 200, 300 dimensional vector for each word that says something about the semantics of this word. This you can use to feed back to add more. One pointer. For exactly this, we used a tool called word2vector. This was done by a man called Thomas Mikolov. He was at Google when he did it. He's now at Facebook. Before that, he was at Microsoft. So he's doing the rounds. But the tool is on Google Code, so it's not on GitHub, so I lied. But the good thing about this is it will train this type of model on unlabeled text. So you don't need to go through the hoops of Wikipedia to find labels of this. You just give it Norwegian text, anything you can find. So we found about 2 billion words of Norwegian text. And this tool will chew through this. This ends up being, I cleaned the data a bit, and you end up with like a 8 gigabytes text file of 2 billion words of Norwegian text, all the newspapers since 1980, etc. And this tool chews through all of this in about 2 hours on my off-the-shelf computer. This is why I said it's not really big data, because if I can go to your average brick and mortar store and buy a computer to do all this in 2 hours, I can't really claim it's big data. But it's still pretty big. It's more than you'd like to read by hand. Anyway, then you can go back and you can feed in these word vectors. So you put in the word vectors as feature representations into this classification problem. So you say, well, I know Geneva has this random coordinates in this space. This is then good for the algorithm, because then, although it still doesn't even know what Geneva means, it can look it up in the space and it can find related words that are similar to Geneva. This means it will generalize better, so that if it, instead of saying gave a speech, it said gave a presentation, the algorithm should be able to generalize from this one sentence to the other sentence that uses a synonym. And we put together all these I think we had 700,000 training examples from Wikipedia. You mark up all the features like this, and you feed it into a machine learning algorithm called a conditional random field. It's about 10, 12 years old, maybe. So there's lots of good implementations of this, also on GitHub and elsewhere. Here's a selection. They're all pretty good and should all be able to chew through this Wikipedia example with no problem. They're all free. And there you have it. And then you will get a classifier given, there's a slide missing. And what they will do is they will go through all these features, and it will learn types of rules, sort of. They're not really strictly rules, but it will learn evidence from the features you have. So for instance, if the last word was capitalized and was the beginning of a person name, and this word is capitalized, it is probably the surname of the person. So if you just saw Barak and now we see Obama, it starts with a capital letter, it's probably his surname. Or if the 2 preceding words were stayed in, it is likely that the next word is location. And they will learn this type of, it will collect evidence from all the different training examples and put it together like this. Essentially they're not really rules, they won't spit out all the rules, it will just spit out weights. It will say, if I see this features in this position and this feature in this position, then add a tiny bit to the weight. And in the end, it will do rules like this, but it will do millions and millions and hundreds of millions of these rules. It will have a massive weight vector and look it up. And it sounds like it will take forever, but again, training this in Wikipedia takes not much more than like 3-4 hours. And then you have it. So then you have the tagging API. Similarly, we built some classification work in Orbit. I'm not going to go into the same amount of detail as I did with the other example. This is just classification. It's a very straightforward machine learning problem. If you've done any machine learning course or anything, you will have touched classification. And here there's lots of really good tools available. This is just a pointer if you'd like to look at something. One of them is scikit-learn, which is a Python toolkit that has support really for many different types of machine learning. And it's quite mature. It will implement only things that are so well researched and known to work really well. It's excellent for trying different things very quickly, setting up different experiments. The other one is a tool called Valpelvabbit. Valpelvabbit is another one, is a tool from Yahoo and Microsoft Research. It is very, very, very fast. It does what is called out-of-core learning, so it's tailored for when you have more data than you have memory. So there's really, Valpelvabbit will just do bits. It's what is called online learning, so it will just learn from bits of your data at a time, so you can give it as much data as you want. And so there's at least blog posts of people who are saying they had to chew through 11 gigabytes of text files, no problem. But really, there's no limit. They can chew through almost anything. So yeah, what we did was I experimented with scikit-learn to find out how it works well, and then use Valpelvabbit to really to do it and put it into production. Of course, now I said you can do all this yourself. You can go to GitHub and download it. Of course, part of the point of starting here is that you don't have to, because we already did it. And hang on. We have Orbit. Here, this is our Orbit demo, so I can type in here a bit of text. So I can say, this has to be Norwegian, because Orbit is only trained on Norwegian text at the moment. So you type in, I like politics, said Solberg to VG. I didn't test it now beforehand, because I like driving without a seatbelt. There we go. And it will go through the text, and it will find here that Solberg, in this case, is probably a person, and VG is probably an organization. And in Orbit, we did one more step that I didn't talk about today, but we went back and then we linked it to Wikipedia. So if you mouse over Solberg here, they will say this is Solberg, and in this case, it's Erna Solberg, the Norwegian Prime Minister. This is interesting, because if I then go here and change it, and I say I like rally, and go again, Orbit will understand the context of the sentence, and it will say, I found this person, it's called Solberg, but who is it really? And he'll look at the words that appear in the context, and he'll compare it to the context of links within Wikipedia, and he'll find out that in this case, it's probably Petter Solberg and not Erna Solberg. He's a famous Norwegian rally driver. Right. So I should have more slides, because I'm nearly done. That's it. Any questions? Can you do it again half as fast is not a question. Go on.
Who are the potential customers? I read it was maybe people writing books or researching, etc. You talk a little about who's going to use this system in their
right. So as I said at the start, I come from Bakken and Beck. We work a lot with the Norwegian media companies. So part of so our initial customer base is exactly this: newspapers and media. And we feel that because media is currently so struggling, they need to maintain page views, they need to keep the readers more loyal. And I think there's a lot of them for them to be gained by having more intelligence in their system. In fact, I'm very glad you asked us this question, because we prepared a little demo that we called Orbit News. What we did here was we crawled the RSS feed of NRK, the Norwegian main newspaper, and we got all the RSS feed for a couple of months. I think it was October till February or something last year. And we ran all the articles through Orbit. And this means that what you can do then, you can automatically generate like a portal for each entity you find. So for instance, this is Barack Obama. And here you can see this timeline. When was Barack Obama in the news? You can here look around and see what happened, and then you get the actual stories or the snippets of the stories from the RSS feed. You can look at what is called the co-occurrence, what other people occurred along with Barack Obama in this period. So if I go to, for instance, where's Putin? There's no Putin. If I go to Kyiv, and we see this as a potential way, for instance, that for media companies to sort of activate the archives. Like NRK, for instance, has archives going back ages. Aftenposten, they have digitalized all their old archives, but it's very difficult to get to them. And it's not really like you go to Aftenposten because you click on the link on Facebook, but then putting the story that you're looking at into like a context of all the news is something they're not very good at. And we think Orbit or this type of technology is something that could help them do this. So, yeah. Any other questions?
Kind of ties in with this, I guess. Do you have kind of no way to know how to weigh new knowledge against old knowledge? Say recent news articles versus really old.
So I don't. Maybe two parts of the question, or the two parts to the answer. One is this finding new entities in text. It's easy enough finding Barack Obama because everyone knows he exists and everyone.
Say there were two people named Barack Obama.
Right. So one part is that Wikipedia updates over time. So you will learn it from Wikipedia again, or like we periodically re-index Wikipedia. So if Wikipedia is updated, then we are updated after a short break. But this doesn't really answer. If the new Barack Obama came straight away, then it's problematic for Orbit to try to figure out that this new Barack Obama, that is not the old Barack Obama, to matchmake this. Then it's probably likely to match it to the wrong Wikipedia article. The other thing that when you match the Wikipedia articles, you don't have to find a match. So part of the reason we go through all these hoops with these word representations is so that Orbit is more clever than just learning a list of names and a list of places and a list of locations. So it's not just based on knowing that Barack Obama is a name, it is really uses linguistic hints from the sentence around this to say that this is a name. So even if there's a brand new name we've never seen before, if the sentence sort of makes sense that this should be a person name in the middle, we will still detect it as a person name. And I mean, the Barack Obama example is evil because he's very popular, so it's very easy to say Barack Obama is probably him. But if it was some random name that was not already taken by a famous person, we would find it and we would say we can't find a good Wikipedia match for this, but we believe this is a person. Here you go. Yep. There was.
Yeah, this is super cool. I'm just and you mentioned using Wikipedia articles and news articles basically as your data source.
Yes.
Which other data sources are you looking at or trying to integrate? And in particular, I'm really curious about stuff like user-generated content and Twitter messages and comments on these articles or something. How would that affect these rules? I guess the syntax would be way different. The grammatical rules will be different. I mean, how you told?
There's two parts of the training. There's one is this unlabeled text, this learning these word representations, positioning them in space. This is just based on any text we can find. It is partially something called Norsk Avis Corpus, which has the text of all Norwegian newspapers from quite a while, and partially based on something called what is it called? Novak, Norwegian Web as a Corpus, which is a massive collection of all. It's essentially a web crawl of everything with a .no domain, including a collection of erotic novels. So in there's everything. Also tweets and also user-generated content and also just spam. And the other part is the Wikipedia, the actual supervised learning of this tagging. And there you're right. This is based on Wikipedia. I think people on Wikipedia write in a certain type of language. They try to sound encyclopedic. If you go and apply the same thing to tweets, it is likely to suffer a bit, the performance, because Twitter messages have different different syntax, different vocabulary. There's more abbreviations, etc. The good part is that you could. We haven't done this yet, but so I'm speculating. But I think you can start with the model trainer Wikipedia, and then you could probably adapt it to tweets by taking a smaller corpus of tweets, not 600,000, but if you were to tag a few thousand tweets, you might be able to learn some of the special language used in tweets, I think and hope.
Really cool. I was just wondering, the n-dimensional vector space, does that work so well that there is no use for any logical descriptions, for example, in description logics where you have taxonomies of stuff, or are there any existing logical descriptions and taxonomies that you could go ahead and use?
So Orbit doesn't. I did some experiments with using part of speech tags. It's not quite a taxonomy, but it's all saying this is a pronoun, this is a noun, this is a verb, and adding these as features. But actually, I think what comes out of the feature representation, the word feature representation, is actually. So it contains the same information as the part of speech tags. So it didn't really improve performance by much, and it made it more complicated, so I left them out. I think there are ways of using more complicated structures to make the learning better. There's people who do structured regularization based on the parse trees of the sentences. Again, a simpler method is probably better, so I haven't looked into this. For the taxonomies, I haven't. This is my background. I come from the semantic web world, so this is. But I must confess there isn't much semantic structures that feed into this. The only exception is this for classification. There's something called IPTC, the International something standardization. It's a news codes taxonomy, and then we do classification into this taxonomy, but it's not related to the tagging. Any other questions?
Is there some sort of public demo?
There is no public demo. There is, however, you can, if you go to orbit.api, if you go to orbit.api, orbit.ai, sorry, you can apply for an API key. And then I'll get an email, and then I can send you an API key, and then you can play with it. This goes for everyone, not just for him. Sorry, you can have a special API key. Any other questions? Okay, then thanks a lot, and